Genomic selection is a revolutionary technique in animal breeding that uses genome-wide marker data to predict the genetic potential of animals for desirable traits. It was first introduced by Mollison, Hayes, and Goddard in 2001 and has since transformed livestock and aquaculture breeding programs. Before genomic selection, traditional breeding methods relied on pedigree information and phenotypic selection, which were time-consuming and less precise. Marker-assisted selection, or the MAS, improved accuracy by using specific genetic markers linked to traits, but it was limited to traits controlled by a few genes. Genetic selection, in contrast, evaluates the entire genome, allowing breeders to select animals based on predicted genetic merit even before they express traits. The adoption of genetic selection has been driven by advancements in DNA sequencing, bioinformatics, and statistical models, enabling cost-effective and large-scale genetic evaluations in livestock, poultry, fish, and companion animals. Instead of just looking at an animal's physical traits like the size or milk production, scientists use genetic markers or the single nucleotide polymorphisms to predict which animals will pass on the best traits to their offspring. It eliminates the need for in-depth phenotypic analysis by enabling the quicker and most precise selection of desired features in microbes, in plants, and even animals. Scientists take a small sample of blood, hair, or tissue from an animal and analyze its genes. They look for special genetic markers, or the NSPs, to link the desirable traits like fast growth, high milk production, or disease resistance. A genomic estimated breeding value, or the GEBV, is calculated, which helps the scientists to pick which best animals for breeding without waiting for them to grow up and show traits. Genomic selection is based on several fundamental principles of genetics. A large number of economically significant features are quantitative qualities influenced by a variety of genes and environmental conditions such as crop productivity, disease resistance, and milk yield. Genomic selection estimates the combined effects of these genes by using genome-wide SNP data. The genomic selection depends on the relationship between quantitative trait loci and genetic markers. Even if the causative variations are not directly found, single nucleotide polymorphism in linkage disequilibrium with quantitative trait loci can be utilized to estimate an individual's genetic potential. The heritability of characteristics determines how accurate genetic predictions are. On the basis of genomic information, highly heritable features enable more accurate selection. By integrating genomic correlations, statistical models like genomic best linear unbiased prediction, or BLOP, enhance the accuracy of breeding value predictions by extending conventional best linear unbiased prediction techniques. The genome-wide association studies help with locating important single nucleotide polymorphisms linked to desirable characteristics. The genomic selection uses genome-wide association studies data to improve predicted models but does not require prior knowledge of quantitative trait loci. Genomic selection has revolutionized in several fields by improving efficiency, accuracy, and sustainability in breeding. Livestock breeding. Genomic selection has significantly improved productivity, efficiency, and sustainability in livestock breeding programs. For example is the dairy cattle. It improved milk yield, composition, and other health. Faster selection of high-performing bulls and cows without waiting for progeny testing. Enhanced genetic progress in fertility, calving ease, and disease resistance. In beef cattle, it increased meat quality, growth rate, and feed efficiency. Swine or pigs enhance litter size, growth rate, and carcass quality. Disease resistance improvements, particularly against foreseen reproductive and respiratory syndrome or the PRRS. Sheep and goats. Selection for wool quality, parasite resistance, and meat production. Improve reproductive traits such as lambing or kidding rates. Genomic selection has accelerated genetic improvement in chickens, turkeys, and ducks by enabling precise selection for traits that affect production and health. Egg production, higher egg yield, and improved eggshell quality. Selection for longer laying cycles and resistance to reproductive disorders. Meat production, faster growth rates, and better feed conversion efficiency. Reduce incidence of skeletal disorders, for example, is leg weakness. The application of genomic selection in aquaculture is growing rapidly, helping improve production efficiency and sustainability. Growth and feed efficiency. The faster growing fish with improved feed conversion rates, for example, is the salmon, tilapia, and shrimp. Genomic selection is also used in pet breeding to improve health and performance. For dog and cats, genetic screening for inherited diseases like the hip dysplasia, heart conditions. Selection for behavioral traits and longevity. For horses, improve performance traits in racing, show jumping, and endurance. Cost of genotyping. While costs have decreased, implementing genomic selection in some species remains expensive. Computational complexity. Managing large-scale genomic data requires advanced bioinformatic tools. Ethical considerations. Selective breeding must balance productivity with animal welfare to prevent unintended consequences. Genomic selection has revolutionized animal breeding by improving genetic gain, reducing breeding cycles, and enhancing disease resistance. It is widely applied in livestock, poultry, aquaculture, companion animals. As technology advances, the cost, effectiveness, and accuracy of genomic selection will continue to improve, leading to even greater benefits for animal production, welfare, and sustainability.